So here's a calculator question from Form B of the 2009 AP exam. It was on A, B, and the BC version of the exam in 2009. And the situation that's described is we've got a storm that's washing away sand from a beach. It's causing the edge of the water to get closer to a road. The rate at which the distance between the road and the edge of the water was changing during the storm is modeled by this function here. So that function is measured in meters per hour. So although they don't really label this as a derivative, it is a rate of change, right? So this is a rate of change, and it holds t hours after the storm began. The edge of the water was 35 meters from the road when the storm began, and the storm lasted 5 hours. So I guess this function holds from t equals 0 to t equals 5. And then they were nice enough to provide us with the derivative of f of t, right? So they've taken the derivative of this function and they've provided that for us right here. Now in part A, they ask us what the distance between the road and the edge of the water was at the end of the storm. And so if you're trying to figure out what the distance is after the storm has concluded, you need to know how much that distance changed by over the course of the storm. And so what I realized is I had access to the function that represents the rate of change of the distance between the road and the edge of the water. And so if I integrate that rate of change from 0 to 5, and I did that from the graph screen of the calculator here, if I integrate from 0 to 5, I end up with negative 8.505 meters. Right? This is measured in meters per hour. This is measured in hours, so that result's going to be measured in meters. This is how much the distance changed by. But what's the actual distance? Well, that's going to take into account what it started at. And it started at 35 meters, right? They told us that up in the problem statement here. So if I started with 35 meters, I changed by negative 8.505 meters over the course of the storm. I'm looking at 26.495 meters between the edge of the water and the storm at the conclusion of the storm. In part B, they ask us to use some units and try to interpret the value of f prime of 4 being equal to 1.007. And we're supposed to do this obviously within the context of the problem that we're dealing with here. So I went with the units first, and what I realized was they're asking me about the derivative of f of t. And so I thought, well, if I were to graph f of t, which I basically did have a graph of back here, if I were to graph f of t is measured in meters per hour. So I'd have meters per hour as my units on the y-axis, and then t is measured in hours. So I'd have t on hours on the t-axis. I realize a derivative is a special slope calculation. A slope calculation is going to be delta y over delta x. And so if I take units of y divided by units of x, I end up with the units of this 1.007. So it's 1.007 meters per hour or meters per hour squared. What does that mean within this context? So if you're asked about a derivative's value at a certain location, within your interpretation, you're always going to want to make sure you're referencing. I don't know why I lost my 4 there. That's my fault. You're always going to want to make sure at some point within your interpretation, you're referencing that the fact that we've got a certain value going into the derivative is significant. So this is something happening at the time t equals 4. And what does the 1.007 represent within this context? Well, a derivative is always a rate of change. And in this case, it's kind of sneaky because it's actually a rate of change of a rate of change. So the way that I went about explaining it was the rate at which the distance between the edge of the water and the road is changing. It's increasing by 1.007 meters per hour or meters per hour squared at that moment in time. So when I look to see an interpretation like this, whether or not it's correct, I look to make sure that you have indicated that it's a rate of change of a rate of change. So the rate that something is changing is increasing. So since I'm referencing that a rate is increasing by a certain amount, I am implying that I'm dealing with a rate of change of a rate of change here, kind of like how acceleration is the rate of change of velocity, which is already a rate of change. So kind of sneaky, I did use the word increasing here because that value is positive. Right? So although the distance between the edge of the water and the storm, it's still technically decreasing. Now notice what I said there. I said the distance between the edge of the water and the storm is decreasing because f of t is negative at 4, but you'll notice that the slope of this graph is positive. So the rate that it is decreasing at is actually going up towards 0. So if we get back to what we're trying to do in part C, and this is probably the largest investment of time within any of the 4 pieces of this problem. They say at what time during the 5 hours of the storm was the distance between the road and the edge of the water decreasing most rapidly? Well, they have provided us with the rate that the distance between the water and the road is changing. We want to know when it's decreasing most rapidly. So when is this most negative, or what is the absolute minimum value of this rate of change on the interval from 0 to 5? And so it does say to justify the answer here. If you think about what I did back in part A, here was my graph of f of t. And so I could try to look at this graph and say, well, it seems like it's most negative somewhere in here, right? Somewhere on this stretch of the graph, it seems like that's when f of t is most negative, and hence when the distance between the edge of the water and the road is decreasing most rapidly. But the justify your answer piece here isn't going to allow you to just use a point from a graph to fill the justification requirement. And so what I realized was, since I was looking for an absolute minimum during the storm, I was looking for an absolute minimum on a closed interval. So I realized that an absolute min and an absolute max for a continuous function have to happen either at the endpoints of the interval that you're considering, which in this case was the entire length of the storm, so 0 and 5, or a critical number that's between those endpoints. And so I did have 2 spots on the interior of this interval that I had to consider. I needed to know when f prime of t was equal to 0 or undefined within the interior of this interval. And so I graphed f prime of t. I was trying to figure out when f prime of t was equal to 0, and I got 2 locations where f prime of t was 0. It happened at 0.66 and at 2.84. And so I took all of the accuracy that the calculator provided me with for those intersections, or for the solutions to this equation right here, and I realized that my absolute minimum had to happen at either one of the endpoints or at one of these critical numbers. Now, I labeled this T1 and I labeled this T2 just so I didn't have to continue to list those ridiculously long decimals over and over and over again. But I didn't evaluate the derivative of f at those numbers. I evaluated the function f at those numbers. So I basically did a little bit of work on the calculator for a couple minutes, typed this in, evaluated it at 0, evaluated it at 5, evaluated it at T1, evaluated it at T2, and I realized that my most negative value, my absolute minimum value, happened at T2. So T2 was 2.840383. I wanted my final answer to be accurate 3 digits beyond the decimal, and so I did have to just make sure I answered the question that was asked. And it is looking for a time, right? It's not looking for the most negative rate, right? It's not looking for this number here. That number helped us build our conclusion by just comparing these 4 values at the tail end here, but we were looking for the time when that was decreasing most rapidly, which is at 2.840. And then the last piece here is, it's not that long. It is a little bit goofy because they start talking about a new situation that begins after the storm has ended. And so we're going to have a machine that's going to put sand back onto the beach so that the distance between the road and the edge of the water is growing. And so they're trying to restore that distance. And the rate that the distance between the road and the edge of the water is growing is given by some unspecified function g of p. P is going to be measured in the number of days since the pumping began. We need to write an equation involving an integral expression whose solution would give the number of days that sand must be pumped to restore the original distance between the road and the edge of the water. So what I realized that we had already done in part A back here was we figured out how much that distance changed by over the course of the storm. It changed by 8.505 meters. So I know that 8.505 meters needs to be restored between the edge of the water and the road. And so now it was a matter of trying to figure out what you needed to do with an integral in order to set up your equation successfully. And so G of P represents the rate of change of the distance between the road and the edge of the water, right? That's measured in meters per day. So if I do the integral of G of P with respect to T, this is measured in meters per day. This is measured in days. So taking a product of those is going to give a result that's measured in meters. And so I don't know how many days are going to go by in order to have the original distance between the road and the edge of the water come about again. But I do know I'm going to define 0 to be the time when the pumping began, and X days are going to have to go by in order for that distance to be restored. So if I could figure out what upper limit of integration here ended up getting 8.505 meters restored between as far as the distance between the edge of the water and the roadway is concerned, I'm going to have my result for part D.